So I heard some of the HTML file you cannot access that one. So in the Etherpad, the Roland put the new address for our older material for HTML files. If you cannot access that one from the GitHub, so if you go to the Etherpad, there's a link for material, not material all, but only for HTML day 1, 2, 3. So here's updated. So you can find the material for here. And I just sent the email to everybody for the evaluation form. So you can choose which program you took. So choose one of program 3 or 4, and then there are like some of the questions. So if you before leave the program today, if you can fill it, it will be great, and it also will be very helpful for our funding source to NIH. We need to report about the evaluation form program, and also will be very helpful to develop our the material or develop our program for next year. So this course will be held 2 more years with the NIH funding, so it will be really great. So let's go over the second part for today. So here we go. So we are gonna first we are gonna talk about the 3 ones, the basically the 2 ones. So how to calculate the sample size, and then how to analyze the categorical data. So this part we are not working for the IPRG data set anymore. So sample size calculation is a really common question. So how many sample size we need? So I believe the Olga already briefly mentioned about the effect, depending on their variation, depending on the sample size, what we can address, and so on. But here, let's try to calculate it for your data set. So this is basically the formula, how you can calculate the sample size. So if you look at here, alpha is confidence levels, and then we also need some power, what you expect. And then also we need like anticipate the fold change or desired fold changes. And also definitely this is the main part, how much variation your data have. So this 3 value, you can decide it. If you want 80% power, you can set it just 0.8. And then you want like 95 percentile confidence interval, you can decide it. And then desired fold changes also you can decide it, just 1.5 or 2 fold changes and so on. Anticipated variance is really depending on your data set. Probably you have some idea how much variation with your preliminary data analysis. This is really hard to say what is the common variance and so on. It's really different depending on your data set. Even you're gonna do the same experiment 1 year before, 1 year after, their variance will be different. So this part is main part you have to know from your preliminary data analysis. So if we know these 4 numbers, we can put this one and then we can calculate it. But it looked like not that really straightforward. It will be a little bit calculation. So there is a package power. This is one of the required package what I asked you to install. This one, if you put the 4 numbers, and actually they can calculate. They were gonna calculate for us. So we are gonna practice this part. Okay. So let's go back to the RStudio. So this is the RStudio what we have. So let's call this package first. Library PWR. Okay, I don't have this one, so I need to install PWR. Okay, so if you don't have the package, just review, click tool, click install package, and then if you know the name of the package you want, and then you can install that one. But you guys already have this one. Then I will call this package is ready to use it. Okay, and let's check what kind of option this one has. Here it is. So power calculation 1. They have several examples, several different functions. If you have a ANOVA test, they can calculate it. If you have a chi-square test, you can calculate for power for that test. If you have the proportional test, they can have, depending on what kind of the testing strategy you use, they use a different formula and then automatically calculate this one for you. So let's try to our part. So we use t-test, so we will use there. You can see there are several different power calculations, but we will use the t-test. We use the t-test, and then based on this, we want to calculate the powers. So they show the several options what we can do. Okay. Then first, they need what significant level alpha we want. We want 0.05. Okay, let's just set alpha is 0.05. And then I want to 95% power. So I set up the power. I want to fix my power here. And I want my anticipate log 2 for changes is equal 1. So original for change is 2. I want anticipate 2 for changes. In other terms, 1 log 2 for changes. I set up. And then based on my experiment, my variance is 0.9. But this one, you have to figure it out from your experiment design. So I said my sigma is 0.9. Then we have one more calculation things. Here is, this is the just sample. Depending on they want D value, effective size, based on formula. This is just delta divided by sigma. So now we set alpha, power, delta, sigma, and D values. Then let's use these functions. I used t-test, but 2 sample t-test, and I want this D value and with this alpha and this powers. So let's try to run. It shows if you want 5 significant interval, and if you want 95 percentile the power, and then you want to use t-test, 2-side t-test, and this much D value, you need 22 sample per group. Okay. Everyone get these numbers? Okay. Then I have challenges. I will give you the challenges. So now we calculate the sample size, but with the same function, we can calculate the power if they know the sample size. Okay? Let's calculate the power if you have 10 samples per group with other number is the same, like same significant level you want, same power you want. If you have a 10 sample per group, what is the power? I recommend to check this health file. Probably they have some, you can find some option from there. Anybody get the power with the 10? Yeah. How did you get it? Any? Mm-hmm. How did you get it? What did you change? Perfect. So I will just copy. Then I can change some option. So here, if you go back to the here, there's option power equal NER, and then here n equal NER. So there are two NER, n and power. If we have n value, they can calculate the power. If you have a power value, they're gonna calculate the n. So here in this case, I said here I already give them power, but here I will ignore this is null. And I said I have a 10 sample per group here. Okay. Then I run it. And then say the power is 65%. Is it okay? So in your case, for example, like this one, if you want to use t-test, you can use t-test. But if your analysis ANOVA or something, you can change this one, the power ANOVA test, and then you can change the value, but you need to figure out the sigma value. Okay? For mass spec data, how you can get the variance is also really difficult, right? This is also another from some analysis. So next Monday, we are gonna talk about how you can calculate the sample size. There's also, we made a function. You don't need to, even though you don't need to put other like sigma or something, automatically they are gonna calculate from your data set and then calculate the sample size based on next your experiment should have the same variance as this current data set. Okay, so if your next experiment have a more variation or something, it will be different. However, we assume next your experiment also should have the same variance, then this much sample size you needed. Okay, that is what I did. And then next one is, this is a very simple case, but I just want to show you, depending on sample size, we fixed alpha, beta, and desired for changes, and quite many values we fix it, right? But if you use a different value, actually how it's gonna be changes, I just want to show them. You don't need to type this one. This is already there. If you want to interesting, you can do it. But I just make a little bit code, and then I will try to explain what I try to do. So first, here, instead of the delta is desired for changes. Before I fixed one, but I just changed the 3 different values. I want to test if desired for change is just 0.1, so really small. If desired change is 1, that's a little bit more than that. How it's gonna be changes for our sample size? Okay, so I will test the 3 different delta numbers. And then this ND is just for repeating. I just count how many delta numbers we want to test it. So basically, this is the main one. And then sigma, depending on the variance of your data set, how is also going to be different. So I want to test the different 3 sigma value 0.1, 0.5, and it should be 1. Yeah, 1. So 3 different values I want to test it. So we can see if delta is decreasing or the sigma is decreasing, how our sample size will be different. Okay, and I just make a really empty the matrix because I just want to save the result to empty space and then repeat it. So here ND is number of the delta what I want. So for example here they use first delta 0.1 with the delta 0.1, and I also test if the sigma have a 3 different value. So with the delta 1 they test if sigma is 0.01 how it's gonna be. With delta is 0.01 and the sigma is 0.5 how it's gonna be. Just repeat and repeat. So 3 values and 3 values total I have to calculate the 9 times. Okay, is it correct? Then I just save every numbers and then make a ggplot. Okay, you don't need to worry about this part. And then this is the result. Okay, so if we have, this is the variability. If we have a different sigma values, how sample size will be depending on delta value, right? Means, let's look at this. So here's a small fold changes we want to detect it. Here is large fold changes we want to detect it. Which one is easier? Which one is easy to find the small changes versus large changes? Yes, large changes, if you have a really large, it's really easy to detect it. Small changes is hard to detect. We have more evidence, it's really small changes they have, right? So if you look at this, always large fold changes, relatively we have a quite small sample sizes we needed, right? And then here, if you want to really small fold changes, we need more number of the samples, okay? Then let's focus, let's fix, anticipate the low fold changes. Fix it here. If you have a more variance and less variance, for example, here the purple color is more variance, and then this was a small variance. More variance means they have a lot of the variance. Something is, for example, I have a measure, but this is 1 to 100. It's really wide ranges, right? The other one, the small variance means just 1 to 2. Everything is just between 1 and 2 and 1 and 2. Means they have we have more evidence there should be somewhere there, right? If you really large changes, we have no idea, 1 to 10. So they have a lot of the variability. If you have a lot of the variability, we need more sample to get somehow. So where is the mean location between these wide ranges? That is the concept. So if you have a wider variability, they should need more sample size. It makes sense? So that is a very, yes. So here I made a matrix 3 by 3 because let's try that one. This part? Yeah. So this part, ND is delta, right? I count how many delta you want to test it. So there they count let's try to go back to the formula. So here, let's try to run. I want to set up the delta, and then let's check ND. And what is ND? They have a 7 value. Okay, so this is a sequence. I thought sequence 1 to 0.01 to 0.7. I want to get 0.1 and make a sequence. So 0.1, 0.1, 0.2, 0.3, 0.5, 0.6, 0.7. So if you see the delta, they have a 7 values. We want to test this 7 value. And here we want to test the 5 value. So we have a 5 value. So roof is first, I want to, so 1, 2, and D is a 7. I will gonna do 1 to 7 one by one. The first I should be 1. With I, the J is one of the 5. So 1, I1 equal J1, and I1, J2, I1, J3, and I1, J5, I1, J5. They're gonna repeat the 5 times within this range with the I equal 1. Okay. Yeah. Then for each I value and J value means first delta 0.1, first delta, the sigma 0.1, they're gonna calculate this part. Okay, calculate this part. So this part is calculate the sample size and then add in the one of the metrics. Just subtract the result and then just keep it in the matrix files. The second, when J equal 2, here they use the delta 0.1, but sigma is 0.2. It's the same delta, but different sigma. They're gonna calculate again and then keep it. And so on. So for I equal first I, they repeat the 5 times. Then second I, they repeat the 5 times here. And then for third I, they're gonna repeat 5 times. So here 7 and here 5, total 35 times they're gonna repeat it. So that is a brief idea about that one. And then before I move on to the categorical data analysis, I want to address this issue. So I know always data type is different. So previously, we working with log to intensity, which is some numbers, versus we have some conditions. So condition and versus some numbers we want to calculate it. However, it's not all the case. Sometimes we want to compare numbers versus numbers. Sometimes we don't have any really integer or double number. We have only categorical variable. So depending on that, we have a different analysis method we have to use. So there are a lot of the statistical analysis, but this is I just want to categorize for really basic, the really common analysis. Quantitative response with the quantitative prediction means numbers versus numbers. Okay? That is, we call this is quantitative and quantitative. Then cases we can do the regression model. Maybe you know the linear regression or something. We want to know the correlation. Correlation means we need number versus number. Then we can draw whatever line over there. Second one is categorical response with some numbers. We have some numbers, but output is categorical. For example, it's a very easy case. If you take the blood, we measure some amount of the proteins, then we need to know, so with this protein, this person have cancer or not, right? Output is 0 or yes or no, 0 or 1, dead or alive, just output is some numbers. Then cases, we have to use logistical models. If you have a multiple output, for example, stage 1, 2, 3, 4. If you measure some proteins, but you want to detect the stage of the cancer, we have probably 1, 2, 3, 4 output we needed. Then case, we can use another type of the logistical models. Okay, so this part and this part is different. And then next one is quantitative response with categorical predict. So output is number. However, the input is categorical. For example, what we are doing with the IPRG one, we have a group informations. We know condition 1 and condition 2. Then we measure, and then we have an output log to intensity. Then we want to compare these two between these numbers. So input is condition. We know the input condition 1 and 2 and measure, and then output is some numbers, and then we want to compare. That is kind of the quantitative response with categorical predictor. So if you have, I briefly mentioned, if you have two groups, just t-test or something like this. If you have a multiple group, it will be the ANOVA model or something else. 2 ways, 3 ways, and so on. So one way means this categorical predictor, if they have one categorical predictor, we use just one way ANOVA, means just condition 1 and 2. For example, for each condition 1 and 2, if they have another measure, time point 1, 2, 3, means we have two categorical predictor, time point and condition. Then we have to use two-way ANOVA and so on. So depending on experiment design, actual model should be different, but this is a very brief categorical category for that one. Last part is categorical response versus categorical response. We have yes, no input, and output is also yes, no, yes, no, yes, no. Means we actually don't have numbers. We don't have these numbers. For example, we don't have this number. For example, yes, no, yes, no, yes, no, yes, no. How we can use the t-test? T-test need numbers, right? We want to calculate the mean and everything, but we cannot calculate with the yes, no, right? Then we have to use another analysis. So that is, and at that time we use contingent table, basically counting how many yes we have, how many no we have, and so on. Then based on proportion we can calculate it. So completely different. So basically from the categorical response, we got some numbers, then use that numbers we can do some statistics. Okay, that is one, and then all these sources from this book. This is from the Bremer and Dorjes. I already have a link, and then this is also link from what our programs link there. This is for using R at benchmark, but R part is really small, and then kind of like a little bit old-fashioned one. However, concept is really helpful. Conceptually, when you think about all the distribution things and so on, it would be really great to review for that one. So I will put this one here, but don't take it. But you can see, and then yeah, you can find something. Yeah, this is not mine. It's Olga's one. So okay, then let's briefly work on with the categorical data set. Let's go back to our script. So what we use IPRG, we have already numbers. So for categorical analysis, we are gonna use another data set. This is already there. So now I believe everyone is familiar with the read the data set. Okay, so let's read this data. Everyone has the data? Okay. Let's look at this data set. This data set is from this paper. This is for colorectal cancer cohort, and then they have some information. This is how data looks like. They have a patient ID, and then for each patient, they have information for each patient. So gender, cancer, the colon cancer or rectal cancer, or two different types of the colorectal cancers. And then they also have indicate they have this specific gene have a mutation or not, and they have a history or not for this colon polyps one. Okay, if you see, here, this is just also character 1. This is also character yes or no, and we don't have number. This one is a number 0 and 1, but in this case, this is not actual number we are interested in. This is just yes and no, right? So we are working with this data set, but for review, what we learned so far, I will I'll try to do some data manipulation. So first, always what else I did, always whenever I read the data set, I always check the DEEM. So here, look like there are 78 rows, means they should have 78 different patients, right? Because each patient, they already have some information, okay? And this is, you can see this is the data frame, but I want to check the DEEM of one of the specific column, gender. And let's try to do this. And then they said no. So DEEM is for matrix only data frame. So if you want to set one specific vector, they don't know it because vector doesn't have row and column. They want to know what is row, what is column, but vector they don't have it. Yes. Okay, matrix and data frame. The matrix need all the value in matrix have same characteristics. So everything should have the numeric or everything should have the characters. Okay, data frame, each column should have some character. One column can be the character, but the other column can be numeric, and so on. Okay, so that is the big difference. Yeah. Array one. How I can explain the
An array is a generalization of a matrix. So the hierarchy is vector, matrix, array. Vector has length. The matrix has 2 dimensions, and an array can have as many dimensions. 3 dimensions would be a cube, but you could have many more dimensions. And what we learned is exactly the same. If you have an array, you still use square bracket operators, but then you need 2 commas so that you have 3 dimensions on which to subset.
Okay. Then whenever I read the data set, I always check the unique information because there are really a lot of the mistake. So I want to check the gender first. Yeah, they have female and male. Okay, because sometimes if they have some typo, probably they have 2 different females, 2 different male, then calculation will be different. So that's why I just check it. And then I can check this class of the gender column. That is a factor. They can allow only 2 value, female and males. And then order is female first and then male, based on the alphabetic order for first characters. Then let's try to review what we learned before. Let's try to these 3 things. Let's get unique information and class for cancel and so on. Yes?
When you type D, TCA, and $gender, you got blue as a...
Yes. If you want to, DEEM is basically calculate the number of row and number of column, right? But this is the vector. So if you want to calculate the length of the vector, you can just type the length, and then they can give you there are 78 gender value over there. Yeah, the measurement. Yes. Yeah. So to calculate the size, vector, length, data frame, DEEM.
No, you get the required
No, yeah. The vector cannot calculate the DEEM. DEEM always need the number of the row, number of the column. But yeah. Okay. So let's try to solve the first one. How can I find the unique information in class for cancel? Let's see. Yes. Yes. Yeah, they have two different cancer type, right? There's no typo. They can really good for distinguish to one. And then also let's check their class. So it's the same thing, but just change unique to class. It's a factor, right? And let's check about the another mutation information. Like change BR. Yes, they have 0, 1 value for BRAF mutation information. And then let's check their class. They say this is integer, right? Do you know how we can change this as a factor? So if they recognize this integer, but if you want this is just yes and no, kind of the factor one, we can change this TCGA BRAF mutation column should have to be factor and then just repeat the type, the same columns. So I click it. And when I check again, they said now it says factor, not integer. Okay, then they cannot do calculation plus minus, times or divide. Okay, then I will also repeat, just double check they have what kind of history they have. Unique TCGA and history 1, they have yes or no. If they have history, they say yes. If not, just no. Okay. This is really simple, but I never forget this step whenever I do the analysis. They are really commonly they have typo, NA, and so on. If you doing everything and then report and then you realize there's something wrong again, you have to do it again, and then it's really painful to where's the problem. So I really recommend to do this one. And actually, this data set actually have a problem. So I want to find where is the problem. So we checked gender, cancer, and so on. Let's check how many unique patient ID they have it. So this is what I did. So unique TCA data and then patient ID, the first columns. Okay. I run it. This line. I want to check the unique information of the patient ID. And here they said 74. 74 level, right? I just want to calculate how many unique, just use the length. Within the length function, I just copy this line and then run. They said 74. But if you remember the dimension of our data set is 78, right? What is this 4 rows for? Where these 4 numbers came from? So I want to dig it. Actually, what's the problem? Okay. Here is another function, table. They actually count by each unique information, that specific column, how many measurements they have it. Is it okay? So I just said I want to count IDs. Each ID, how many measurement they have. So I run, and then just look at this one. I expect each patient ID should have one information, but here they do have two information, right? Here also two information they have, right? Two information they have. Then we need to double check. From same patient, they have a two means they have a exactly same rows, or they have a really different number, different value for each patient. It's a really critical point, right? So that's why I did it. So here we are gonna use what we learned, the subsetting skills. So from this the count ID, I just checked the count ID what by value we have. Some patients have one, some patients have two. Then I can make a conditions. If which count ID have more than one measurement, this is this line, and click run, they show 4 ID which have 2 measurement. Okay, means we need to dig in this 4 patient ID. Yes.
Explain exactly what the table does.
This table. Okay, table means, okay, let's just try to do some very simple case. So, okay, here is the patient ID. And then let's do very simplify the gender we have. Okay, this is the person 1. They have female or male. But people 2, they have male. But if they have just repeat it. I just repeat it. And then table means count by each unique PI how many rows we have. Okay. So here in this case, PI should have 2 rows, and P2 have 2, and then P3 have 1.
But if the information is not the same,
Yes, it doesn't matter. They just count. It doesn't. They didn't see this one. They only see this one, and then just count the row. So that's why we need to double check it. So here we have a 4. So what I did, from this specific our data set, bracket and comma, I want to subtract row, which this patient ID equal to this first patient ID. Okay, then I run. What they show the two rows which have this patient ID, but you can see they have a same male. They just duplicate the information, right? But if we are not consider this and then just count, they just add more for that one. So definitely we need to remove this one. Okay, then I will give you the task. Now we have a 4 patient ID. Let's check the other 3 patient information. They are duplicated or they have a different information. Okay, I will give you the 3 minutes for that one. So let's try to do this. So to check the other patient, I also copy the same code, and only I change only this part. I copy this number and then copy here, and then run. It also have a same information they have. And let's check another patient ID. And they also have the same information, right? And then last part, also I change this. Okay. And then they also have same one, which means I want to remove this duplicated information, right? Let's run the new functions. Duplicated, and if they have exactly same row, they're gonna detect it. So duplicated row, if true, means I have another row for that one. I already copy somewhere else. Then this mark means, oops. Okay, I will try that one first. With this data set, it will show any duplicated rows. Okay, let's run this. And then they show 4 runs, which already this information available somewhere else. But we want to remove this. Means we want to keep which row is not duplicated, right? So here I make this mark, okay? Then I override it without this duplicated with our original name. And then if we run, how I can check something is removed or not, I will check the dimension again. Before we have 78, now we have 74, right? Then now we can do, or we can start to do something, okay?
Just don't make that go away again. That part, right? Thank you.
Is it okay? So without this one, all the proportion number or sum of number will be different. So I really want to double check this data set first. Then let's move on to the next one. Yes. We want to keep the row which is not the duplicated. This mark means not. Yeah. Show file.
Data frame.
Data frame.
Yeah, so this is a new data frame, right?
Yes.
The duplicate is removed. Can you
Yes.
go down to the very last one?
Yes. So now you can see they have some numbers like 78, but actually middle of some number is already removed. Yeah. Okay. Then just final check. Again, I just want to double check our patient number is the same as before. So same number, same code. I want to get the unique information, unique participant ID. Here, 34. I also double check. Length is 74. So each sample, they have a 1 row information. Okay. Then let's make a contingent tables. So this is also tables, right? But before, I just use only 1 column information. So for example, here, based on this ID, they count how many rows we have. If you have more one, based on more column, we can also make a different tables. So now only 1 we can count it. If you have a 2 information, 2 groups variable, they can make a 2-dimensional tables. That is a conditional tables. So let's try to do this. For example, here, TCGR CRC1, I want to make a table count for cancel and the history of this one. Let's try to run and let's see how it looks like. So based on column is for each column for different cancel type, and each row is for history. Okay. Okay. I want to double check before I move on. I just want to, here I use cancel and history, but I want to double check. It means if you sum of these two numbers, this is total number of the column. If I sum of this number, it will be total number of the reluctant one, right? Let's double check. I want to draw the table TCGA 1 only by cancel. And here, let's see here. With sum of this is 50. With sum of this is 24. It makes sense? Then, based on these numbers count, we can make some visualizations. The dot chart. So I run this one. Yeah. It will show this plot. So basically from this conditions table, we want to see if any specific cancel type have more history or not, kind of thing we can see. So we expect here column type, there is more number of no history persons, and then here lectern one also they have a more number of the non-history persons there. So short visualization. Then we can move on to the proportional test. So it's a different hypothesis with the t-test. T-test want to compare mean value, and then they have a difference between two groups, the means. Here, the hypothesis is true to each population. They have same proportion of another the population, another category. So they have a same proportion or not. Okay. So that's here is things. So let's check what our conditions table. So here we have this information. So this is the prop test is a proportional test functions, but we need to put two numbers, which means first number of count what we want to look at, and then total number of the count. Okay, so here let's run. So call it a cancel polyp data set. I want to extract only second row. Second row means this row. I want to calculate the proportion of the history among the cancels. So here is I want to get the polyps. Then polyp number will be this person who have a history, and then I want to calculate the total number. That's why we can calculate the proportions. Some numbers versus total number will be proportion. So here I used apply, means if I can apply this specific function by column. So 1 is row, 2 is column. They want to calculate the sum by each columns. That is the things. And then if you put these two numbers, now we can get this proportional test. So it said this is the two sample test for equality of the proportion, and then here is the chi-square number, and then this is the p-value. And then what was the alternative hypothesis is for the two side one, and then here's the confidence interval. The format is quite similar than the t-test. Okay. Then this is also same as what we did to the t-test. PT names show what kind of output we can extract from proportional test, and here is the estimation for each group proportion and test statistic and geographic freedoms. Okay? Yeah. Sorry? Apply functions. So here, cancel polyp is tables. So apply function means I want to apply this specific function for this data set, but apply for each column. So 2 means columns, 1 means row. Okay, so if I run only this part, you can see they sum for each column. Okay, and if I change this one to 1, they just sum for each row. So they sum for row no and yes. Okay. For proportional one, we also can test independence. It's a chi-square one. It's more simpler. Just chi-square and then just type your data set. It's much simpler, right? Then this chi-square t value, let's remember 2.32. And then our original proportional one, this one is a 2.32. And actually they have a same background when they calculate it. I just want to mention that 4 different test one. First one, proportional one, chi-test, and Fisher test, and G-test. There are several different type of this. But actually, for background itself, their methodologically is similar. And then this one is also Fisher test. Also same thing. They want to test they have any relationship this 2, and then they also can show you the p-value and so on. But this one is non-parametric method one. Then I will give you the task one. So before we compare cancer and history, they do have any relationship. Let's compare if gender is really matter. No, the proportion of the male is matter between the cancer type instead of the history. I will give you the 5 minutes for this. Okay, so our goal is want to compare the proportion of the male patient among the all colorectal cancer sample is different from the proportion of the male among the rectal cancers. So first, I want to count. I want to make a table between the cancer and genders. So I just copied what we have here. I want to make a table first. So gender, based on gender and cancer type. And then I made a new variable, so cancer and gender. And run. And it shows these tables. So if you look at this, for colon cancer, like most likely half is gender, like the female and male. And then like the vector cancel is almost not that helpful, like quite similar to have somewhere, right? Then instead of this one, I also change this one. The male, I want to get calculate the proportion of the male among all. So male is in the second row, so it still have a second row. And then I will put this is a males. Then it shows there are 26 male for column and then 14 male for vector cancels. And here I also change this one for gender. I want to sum by column from these tables to calculate the whole number of the cancel by different types. Then I will calculate the male, change this male, and then they show the numbers like this. And they said the proportion is 0.52 and 0.58, and based on their testing, they are not different. Yes?
So the cancer apply part, we could have left it as it was because it was summing the same centimeter, right?
Mm-hmm.
It sums how many people have cancer.
Yes. Yes. Which one?
So we didn't have to put
No.
cancer.gender, we could have left polyps.
Exactly. Same.
Because
Exactly.
in the end it gives you how many people have cancer.
Exactly. We don't need to. Yes. Yes. So there is a things. So none of them are related because I know the reason why. Because this is already published the data set. They want to compare some different one. So when they make a design of experiment, they actually sample same number of the gender, try to make the similar number of the gender, similar number of the history to compare that one. So that's why here in our data set, we cannot find it. However, if you just randomly select from whole colorectal cancer versus other one, probably they can have some different numbers. So this is the main things. So whole things what I at least I know 2.5 days is really short to cover all catch up all our things, but at least my minimum, my desire to deliver is start to R and then not afraid of to use R, and then can calculate the very simple things and like any very simple random things, and I hoped you can find the function what you want, and then I want to teach how to use the functions and how to get some output that specific function, because we cannot cover all the type of the analysis, but it will be really different. So if you know how to searching and how to read it and how to find the option, I hope it will be at least it will be helpful to you can start to do something else. So that is the main one, and another one is more statistical part. I want to deliver different data set. You have to use different statistics. So I know t-test. So I want to t-test what data I have. But you have to know, depending on your data set, you have to use different method. And that one is I want to deliver to you. So that is actually main part I want. And then last part, what I want to do is a little bit more complicated. So if people are not confident about this one, just listen. But if you want to learn more about this, just you can follow this one. There is another type of the test for proportional one, but that is when we have a large number of n, we can use this one, because I type it here, large sample t-test. If you have a large number of the sample, we also can, this one is more close to normal distribution one, then we use this normal distribution for our calculation. So that is a background, but not always this type. So you have to choose based on your experiment, you have to choose different one. But for this test, at least I know there is no function in package, means we can make the function based on these equations. Okay. The good thing is we can use already established developed function, but if you have very routine task and if you can make the function, you can use this function for your own work because you don't need to type every time. You can just call that specific function name for that specific task, and then you can very simplify your line. Okay, so that is my goals. So let's look at this. To calculate, based on methodologically, this is the equation, what we can calculate it. And it looks complicated, but we can type it, right? This is a fraction. This is upper side and then lower side. We need to type this one first and then type this one later. I want to make a function to calculate this g-score. So here is the function is to make a function. Okay, so now I want to make a function named g proportional p, and this specific function need 1, 2, 3, 4 input. x1, x2, and 1 and 2. Why? Because I want to calculate the proportions. Proportion p1 equal x1 divided by n1. This is the proportions. And p2 also calculate by x2 divided by n2. So if you have these 4 numbers, first we can calculate the first proportion. P1 is x1 divided by n1. P2 is x2 divided by n2, right? And after we calculate this P1 and P2, I want to calculate the numerator. So let's look at the numerator. This one is just P1 minus P2, right? So here I just make a numerator is P1 minus P2, okay? And then I want to calculate the P is common. This is kind of the combine of 2 proportions, and this is the formula, okay? So P common is x1 plus x2 divided by n1 and 2. So this is exactly same as this one, right? Just step by step, I just calculate it. And the denominator here also basically this. First square root, and then p common, this p common, times 1 minus p, and times this number and this numbers. So exactly, each one is exactly, I just calculate step by step. And final g-score is numerator divided by denominator, right? So here, our statistic, g statistic is numerator divided by denominator, right? Now we have a g-score. And with this g-score, I want to calculate the p-value. That is what I just briefly mentioned at the last section, last part of section, based on something I just calculate the p-value. Then here I will return this p-values. Okay. Then now this function always need this 4 input and then return the final p-value. This is this function's job. Then I will use these functions and then I put exactly one value by one. So for example, cancel polyp 2.1. Cancel polyp is here. 2.1 is second column, second row, first column, 21, and so on. I just put this 4 number and here, and then they just calculate the p-value. So this is how we can make the function one. Okay. Then I will practice one very simple. I will try to make one simple functions. I want to write the function name f to c, means I just convert a function to temperature from Fahrenheit to Celsius. Okay, and this is the formula f to c. So let's try to make a functions. So f to C, I will make a function. And this variable should be functions. And within this parenthesis, I need the input. I said I want the Fahrenheit to cover C, so I said the Fahrenheit. I need the Fahrenheit temperature. Then I will return the Celsius temperatures. Okay. Then this bracket. Okay. Between this bracket, I can make the functions. Now I want to calculate the new Celsius numbers. Celsius, how we can calculate it is Celsius equal F minus 32 divided by 1.9. Okay, just exactly type. I will type it. Fahrenheit, we already have this Fahrenheit number minus 32, but I need this parenthesis and divide by 1.5. Okay, means if we have F value here, we can calculate the C values, right? Then what are you going to do? I will return C. Okay. Okay, select this 1, 2, 3, 4, 9. I will run. Okay. Then our environment, we have a data, we have values, and we have a functions. New function is ready to use it. Okay. Then what I'm gonna do is, okay, I want to know Fahrenheit F2C. What is the value? Okay, what temperature is now? Like I guess 75. And what is the Celsius? 75 Fahrenheit. And then show is 24. Okay. So this is just a very basic form. So it can be very complicated inside of it, but it can be simple, or whatever is really routine job, you can make these functions. So this one is on all material. What I prefer to this section. We have a 5 minutes left. If people have still some energy to work with, I will recommend to make a new function, C to F. If you put the Celsius, how we can calculate the Fahrenheit.
with I6 phase. So it means there is a lot of code. So let's see. Oh no. See, if I wanted to do six plays, well, that is because it iterates. So this function is run. Yes. The first one is wrong. It's wrong with values.
I just wanted to know how long when I go back, how long I have to
It's different.
Okay.
So when you do the first policy,
I mean, first the time it means that it
Oh,
goes
and
through
if we have
everything
questions, we
that
can
you
just
need
email
for the
or?
oh, so you create the policy. Okay.
For this course, probably one month, or the other course, like regional advanced, if you go through the
Yeah.
advanced, maybe Kylie or something can do in
Okay. And then Kylie is the one to talk to about Cardinal.
she's the professional.
So I made my own correlation matrix. This is my own project. It's a spectral count. So I just
Yes,
wanted to
okay.
decide whether my correlation is the statistic is. I think just based whether it's appropriate.
Are you gonna come to next week too? You're gonna cover the spectral
Okay.
context. So imagine only you read your data, the row that you get something, and then make this one, and then yes, this is function. Here's the function. This is not your script.
Yeah.
Yes. So we are gonna cover that. Yes, briefly before spectral. Yeah, maybe you can see.
Okay.
Have you tried this code?
So you're most
No.
likely to
Yes.
Because
But there are different kinds of correlation.
Yeah.
Doing correlation.
yes.
that's the only increase to
And then
six
make
is
this.
Yes, exactly.
Just
But
platform.
Yeah.
Yes. You have quite experience. Isn't it too boring for this course? You already have this one means you already have a lot of experience.
I don't
It's okay
think it
because
worked.
most of the time I just look at it in the net.
Right? This hard.
Yeah. So yeah, but there are other things that okay, that's how you do it because you don't see everything. Yeah.
I think we never can catch everything.
Yeah. So when I just need something, I just learn that.
I did too.
And anyway, I'm not very good at statistician or whatever, so I don't really care much about others.
So then, what is your main project? What is your main research?
Usually I'm in molecular biology, so I do the genome editing stuff. But now I'm working on mass spec. Actually, I started learning mass spec. I started by really doing the benchmark, the sample prep, and also upgrading mass spec.
Oh, you already have this one. This is really quick.
Yeah. Our technician is. I also ask help from our technician. I don't understand anything because our technician is a programmer, developer stuff. So, but he's working on Python. Actually, I'm also doing some small Python thing, just to, because especially the very first challenge for me was when you have the CSV. How do you extract the data from CSV? So I actually made everything in Python because that's what the technician knows really well. So I extracted all the CSVs from Python. But it seems that the R is also quite easy to So I was like, the making of contingency table and extracting the data from the sets of data is really the most challenging, I guess, for beginner, because you want this and that. Yeah.
But if you understand this one, you already go on to the next version. You pretty much generate every article by yourself.
Yeah.
Then what do you want to get from this one? What do you want to know from this one? Just core courses. What is your goal? Yeah, because it's
I just want to make good
good things. Good things.
That's what I like. That is just what I make good figures and good statistics. That's it. No, kidding.
Don't hesitate to swap the course.
So it works on my computer.
Are you gonna stay here before?
Yeah.
So whenever something
I have tried to think
So next week, another one is more.
you show me the output of session.
The other one.
Yeah. Others, some of it very similar. Doesn't really. But I think for me the most difficult part is to make the files.
And also methods.
Yeah.
Yes, you have a lot. I don't want to waste your time to do it.
No. It's really at least the fundamentals. When you look at the net, it teaches you how to do this. You can do it generally, but since I don't have any
How it works. The conditions that you are trying to use to calculate lead to
I just summarize by myself, but I don't know if this is readable.
there was this function you used that was called how to sum itself that itself calls me a function. And because of the inputs, the values in that function are wrong.
that if we have this problem, then
Yeah, I would need to understand, I would need to look into details to understand why it fails. using a function. It's telling us how much which does the same thing. The difference is that it doesn't take the d. It takes the delta is the difference in standard deviation. Power. It has also the significant values so that the difference is identified.
Oh yeah.
So this is
Oh, we need the column, right? But then it should give me just the value for
what has changed is the use of the function apparently does not solve. So the implementation of the function is different. But there's a difference between no, they should be exactly the same result. But sometimes you have different ways to calculate the same thing. That becomes very technical, but so for example, if you do principal component analysis, you have different ways to calculate components.
Got it. Okay.
And some ways are maybe faster than others, and some ways are less stable.
Check this column.
And you could have action cases where the code fails because they have to do mathematical operations. So imagine there is a log somewhere in the function. If the function calculates a log, and somehow your input generates a negative value, and they try to calculate the log, and it fails. Whereas another implementation does not use the log. So I always use power, I never use either draw. In theory, they should use power, yeah, the function power test. Is in the stats package, which is now it is still quite surprising that in your computer PWR t-test things. I know I did not try that. No, I didn't know about that. Okay, so if I use 0.8, so there is a